Okay, so here we have a block traveling at 12 meters per second across a horizontal surface, and we're given the coefficient of kinetic friction as 0.2. We're told that the block slides across this horizontal surface and comes to rest at an unknown distance from the starting point. And from this information, we're asked to solve for how far the block slides. This problem is solvable with forces. What we could do is take the Newton's second law approach and do free body diagram, which we're going to need. So let's go ahead and do it. So the forces acting on this block, we have mg down, we have normal force up, and we have friction pointing opposite motion, parallel to the surface. And friction is mu times normal force. So one way to solve this problem is to do free body diagram, summation of the forces, solve for the acceleration, and then use a kinematic to determine how far the block slides. But we're going to do this problem using work and energy. So over here on the right-hand side, I have just a summary of conservative forces and non-conservative forces. What we mean by conservative forces are gravity or springs. And if gravity and spring are the only two forces affecting the motion of the object, then mechanical energy initial will be equal to mechanical energy final. And as we talked about in class, there are three forms of mechanical energy. We have kinetic, potential of gravity, and potential of spring. So basically our initial mechanical energies added up will equal our final mechanical energies added up. And a quick example of this would be like, here's the ground, and then a ball gets dropped. So there's a ball up here starting from rest. V initial is 0. The ball drops down to the ground. What's the velocity right before the ball hits? And let's say we're given the height, let's just say 2 meters. So for a problem like this, you go through your energies. Because the ball starts at rest, kinetic initial is 0. I would say the 0 point's down here. The 0 point is where we measure h from. So the ball does start with potential energy because it's above the 0 point. There's no spring energy, so we cross that out. And now we go to final energies. There is kinetic final because the ball is moving. There is no potential of gravity because the ball has come to the 0 point. And again, there's no spring. So what we have is gravity is the only force affecting the motion of the ball. So we have potential of gravity initial gets converted to kinetic final. And then from here, what you would do is, plug in the equations. You would say mgh equals 1/2 mv squared. M's cancel, and then you could solve for v. So that's just a quick example of a situation where there's only conservative forces. Now, non-conservative forces, this is when there's a force other than gravity or spring doing work on the object, and that's what we have here in this problem. The non-conservative force is friction, and because friction is present, what we said up here is no longer going to be true, because non-conservative forces will make the initial mechanical energy no longer equal to the final mechanical energy unless we account for it. So that's why we have here this plus or minus work non-conservative. It's plus or minus because non-conservative forces can add mechanical energy to the object, and non-conservative forces can remove energy from the object, such as friction. So our master equation, which we're going to be using in this problem, is this. And pretty much this is the equation to know. And if you happen to have no non-conservative forces, then you could just leave out non-conservative forces. Okay. All right, so let's make some space, and we're going to solve this problem. All right, so, oh, actually I should have left that. Here, I'll write this out again. So our master equation is kinetic initial plus potential of gravity initial plus potential of spring initial plus or minus any work non-conservative equals kinetic final plus potential of gravity final plus potential of spring final. All right, so looking at this situation, the block starts with kinetic energy. So let's put that in blue. We have kinetic energy at the start of this problem. And the reason we have kinetic energy is simply because the block is moving. There's no potential energy at all in this problem. There's no potential energy of spring. There's no potential energy of gravity. There's no spring energy simply because there's no springs. And there's no potential energy of gravity because there's no change in the vertical height. The only time potential energy of gravity becomes a part of the problem is if there's some sort of vertical height that's involved. And in this problem, the entire situation is on a level surface. So there's no change of potential energy of gravity. The entire problem takes place on the 0 point. So over here, if we go through our energies, let's look at the block over here at the final point. So the velocity is 0, which means that the kinetic energy is 0. Put this back to black. So the kinetic final is 0. The block stayed on the 0 point, so there's no potential energy of gravity. And again, there's no spring. So our total mechanical energy final is 0. The block ends up with no mechanical energy. Now if we look over here at the initial, we do have kinetic initial, but we're not able to calculate exactly what it is because the mass is not given. We do have it, so I'm just going to write 1/2 mv squared. And I'm just going to mention whenever mass is not mentioned, so you read through this problem, the mass of the block is not given, which means it's not going to matter. When we start setting up the equations, the mass will disappear. Okay, potential energy of gravity, 0, because the block is on the 0 point, and there is no spring. So basically what's happening here is we're starting the problem with kinetic energy, and then the block slides over to here, and we end up with no mechanical energy. There is 0 mechanical energy final, which means all of our initial mechanical energy was taken by friction. Friction steals mechanical energy and converts it to heat. So let's go through this master equation, and then right here we have work non-conservative. I'm just going to change that to work of friction, because in this problem the non-conservative force is friction, and it's going to be negative because friction always takes energy. It's going to remove energy from the initial mechanical energies. All right, so going through our energies, we have kinetic, we do not have potential of gravity, we do not have potential of spring, and then as we talked about, all of our final mechanical energies are 0. They all go to 0. So what this leaves us with is kinetic initial minus the work done by friction equals 0. Or in other words, the work of friction is equal to the initial kinetic energy. The starting kinetic energy is equal to the work of friction because friction takes all of it. Okay, so now what we do is we plug in our equations. The equation for work is force, which is friction, times distance, or displacement, which is delta x. And then kinetic energy is 1/2 mv squared. So don't worry, this mass is going to cancel. Now, we have to say something. We got to plug in for friction. So if you remember back to the chapter on forces, the equation for friction is mu times normal force. So that's friction. Friction is mu times normal force. And then bring down the delta x. and then this is equal to 1/2 mv squared. Now, we have to figure out what the normal force is. So you learned how to do this back when we did forces. So looking at our free body diagram right over here, looking at the free body diagram, we're going to sum the forces in the y direction, which gives us normal force minus mg equal to ma. And there's no y acceleration. The block is not accelerating vertically. So if you rearrange this, our normal force is mg. So we're going to take that and plug it in up here. So now what we have is mu mg times delta x equals 1/2 mv squared. So at this point, the mass drops out. M is on both sides, so we can cancel the mass, and now we can solve for delta x, which is how far the block moved. Oh, and one thing I forgot to mention, back up here in the work equation, the key thing with work is that the force and the displacement have to be parallel to one another, which is the case because our friction force right here is parallel to the delta x. They're parallel to each other. All right, so doing the algebra, we get delta x equal to v squared, which is, that's v initial squared, divided by 2 mu g. So this is 12 meter per second squared divided by 2 times 0.2 times 9.8. And then this gives a delta x of 36.7, which is how far the block slid as it came to rest.